All right, y'all. In this video, we are going to move into the second section of chapter 6 that is titled Volumes. So last video, we did area between curves. Now we're going to talk about how you take area between curves and convert it into a volume or a three-dimensional shape. So let's talk about the formula so we can find volume of a curve. All right. So let S be a solid that lies between two parameters, x equals a and x equals b. If the cross-sectional area of S in the plane P sub x through x is perpendicular to the x-axis is a of x, then where a is a continuous function, then we can define the volume in the following way. So in the book, they define volume using the limit definition that we covered back in chapter 5 a little bit earlier in this class. What we want to notice here is that when you want to find volume, pretty much the easy way to think of this is that you need to take that area problem and you need to integrate it with respect to x. Now, the difference is that since we're going to be revolving these regions around lines, it depends on what kind of shape you have as to what your a of x will be defined as. So, when it comes to solids of revolution, if the cross section is a disk, then we find the radius of the disk by using the following formula. We would define a of x as being pi times the radius squared. Now, this is the formal definition of what we call the disk method. A way that I usually tell students when they're doing disk method is that essentially there is no gap. So the axis that you're rotating around and the function that you're given does not form a gap, and we can use the disk method. When you plug this area formula into your integral, remember pi is just a constant, you can actually write this as volume equals pi times the integral from a to b of the radius function squared dx. Now that would be if you're doing it in terms of x. It's the exact same formula if you were to do it in terms of y, only you would have to do everything as a function of y. But the pi you can just factor out front, and then you would put the radius squared. And keep in mind, radius is pretty much the same thing as f of x in this case. If you are doing what we call the washer method, so if the cross section is a washer, we will need to find what we call the inner and outer radii and subtract the area of the inner from the outer disk. So your formula for area that you're going to end up integrating would be pi times the outer radius squared minus the inner radius squared. Since pi is once again just a constant, you could factor that pi out of your integral, and then you would take your outer radius function and square that minus your inner radius function squared. And once again, this can be done in terms of x or y. And when we say outer and inner, outer is the further function from the line you're rotating around. Inner is the function that's closest to the line you're rotating around. Now, essentially, like I said, when you do the disk method, there is no gap. The time that you'll know to do the washer method is if there is a gap in the area that you're revolving around the axis and the line that you're rotating. And when we go into these problems, I'll show you what it looks like when we get into a disk method or a washer method. So let's look at our first example. I want you to find the volume of the solid obtained by rotating the region bounded by the given curves about a specified line. That's going to be the same instructions for every problem we do today. If you're given the function y equals the square root of x minus 1, and it's bounded by y equals 0 and x equals 5, you get this little black shaded region. We want to revolve this region around the x-axis. So when you set this up, the first thing I notice is that if you are revolving around an x-axis, you must do everything in terms of x. All right, so everything's in terms of x. The axis that you're rotating around, there is not a gap anywhere between the axis and this black shaded region. So for us, that means that we are going to do the disk method, which is pi times the integral from a to b of your radius squared with respect to x. So when you plug in your information that you're given, you would do pi times the integral from a to b. Your a and b have to be in terms of x. So if you look at this black region right here, it is bounded between x equals 1 and x equals 5. The radius in this formula is just the original function. So you would take the square root of x minus 1, square it, and we're going to integrate this in terms of x. Well, it's nice here, even though it was a square root problem, when you square a square root, that goes away, and you get the pi times the integral from 1 to 5 of x minus 1 dx. And now it's the same kind of problems we've been doing for the last few sections. You can add 1 to the power and divide by the power. So that's x squared over 2 minus x evaluated from 1 to 5. And then you would end up having pi times, that would be 5 squared over 2, which is 25 halves, minus 5. Then you plug in 1 and you would get 1 half minus 1. All right, so then you would simplify by distributing your negative through. So that would give you 25 halves minus 5 minus 1 half plus 1. If you put your halves together, 25 halves minus 1 half is 24 halves, which is 12. Negative 5 plus 1 is minus 4. And if you put that all together, you'll get a final volume of 8 pi units. And just like when we did area between curves in the last video, when you're finding volume, your answer should always be positive. So that is an example of the dis method when you rotate around the x-axis. There is no gap between the shaded region and the axis, so that's why you use the dis method here. Now the dis method can also be used around the y-axis, so let me show you an example of that. So this time you're given the function 2x equals y squared, bounded by x equals 0 and y equals 4, which generates this red shaded region. And this time we want to rotate this region around the y-axis. Once again, you can tell between the red shaded region and the line that we're rotating, there's not a gap. So once again, we are going to set up the dis method, which is pi times the integral from a to b of your radius function, but we're going to do this in terms of y because we're going around the y-axis. Now, the other issue you're going to run into is that you don't have a function of y given to you here, because to have that, you have to get the x by itself in the problem. Well, that's simple enough. You can divide both sides by 2, and you can say that x equals y squared over 2. That's going to be our radius we have to use in the formula. So now I can plug in all the information I have. So my volume would be pi times the integral. Now, since you're going around the y-axis, you have to use your y parameters. So I would be going from 0 to 4 on the y-axis. I would take my newfound radius function, which is y squared over 2, and we're going to square that, and we're going to integrate this with respect to y. So let's go ahead and square that fraction. So we're going to integrate from 0 to 4 of y to the 4th over 4 dy. We can factor that 1/4 out front to make this pi over 4 times the integral from 0 to 4 of y to the 4th dy. And now you can add 1 to the power and divide by the power. So this would be pi over 4 times y to the 5th over 5, evaluated from 0 to 4. I'm going to actually bring this 5 out front because it's just a constant, and I can write that as pi over 20 y to the 5th from 0 to 4, which will give me pi over 20 times, if you plug in 4, you get 4 to the 5th, and then plugging in 0, oops, I'll actually write it out so y'all can follow along, you would subtract 0 from that. All right, so let's see, we got to figure out what 4 to the 5th is. So 4 to the 5th would be, let's see, 4 cubed is 64, 64 times 4 is 256. And then I got to do a little scratch work here. 256 times 4 again would be 1024. So we would end up with 1024 pi over 20. And it looks like both of those share a 4 in common. So I can simplify both numbers by 4. And that should end up giving me a 256 pi over 5. And that is the volume of that red shaded region rotated around the y-axis. And that's also an example of a disk method of on the y-axis. The big thing is that disks can only be used if there's not a gap in what you're rotating around. All right, so now let's tackle the problem where you have to do some washer methods. So we got disk under control. So when do we know to use washer? So find the volume of the solid obtained by rotating the region. So same instructions. This time they gave us y equals x squared and y equals 2x. And we want to rotate this around the y-axis. So based on the picture over here on the right, you get this blue line, which is the straight line. So the blue line is y equals 2x. And the parabola is y equals x squared. The problem here is, though, if you notice, it says you want to revolve around the y-axis. So if we revolve this direction, the reason that this is a washer method is because there is a big gap between the region you're rotating and the axis you're rotating around. So first time doing washer method. So the washer method would be pi times the integral from a to b of your outer radius squared minus your inner radius squared. And since we're going around the y-axis, it's got to be in terms of y. Now here's the other issue. Both of the original functions were given to us as y equals f of x functions. So we're going to have to convert both of these into functions of y. So on both of these, I need to solve for x. So on the first one, that would give you x equals the square root of y. And on the second one, that would give you y over 2. So next to both of these functions, I'm going to put their equivalents. So x would be y over 2. And on this one, x would be the square root of y. All right, so when we go to set up our volume formula here, this would be pi times the integral. Now we're going around the y-axis, so you have to use your y parameters. So this shaded region starts down here at 0, and it goes all the way up to 4. So 0 to 4. So your outer radius, that is the function that is the furthest away from the axis you're rotating around. So the furthest function is this red line. So I have to use the square root of y as my outer radius function, and I'm going to square that. Minus the blue line is the closer function. So that would be my inner radius. So I would use y over 2, and you would square that. And that is your setup. We can square both of those terms. So this would be pi times the integral from 0 to 4 of y minus y squared over 4 dy. And then you want to integrate both of those terms. So this would be pi times, this is y squared over 2 minus y cubed over 12, evaluated from 0 to 4. So if I plug my 4 parameter in, that would end up being, let's see, 4 squared, that'd be 4 squared over 2 minus 4 cubed over 12 minus, and if you plug 0 in, you just get 0 for both of those terms. So simplifying what I have left, you would have pi times 4 squared is 16, and 16 divided by 2 is 8. 4 cubed is 64, so 64 twelfths. I'll actually write that out so I don't mess up. All right, so let's see, 64 twelfths. Both of those share a 4 in common. So if I divide both of those by 4, it would be a 3 on the bottom and a 16 on top. And then to get common denominators, I can rewrite 8 as 24 thirds minus 16 thirds, which when you subtract those two and multiply it by pi, you get an exact volume of 8 pi over 3. And that is an example of the washer method rotated around the y-axis. Now, this is actually a problem as well, that you could find the volume rotated around the x-axis if you wanted to. You would have a different outer and inner function, and you would have to use the original x squared and 2x. And the volume would be a little bit different, but this is a good example where you could do the volume either way. All right, so that's the basic washer. So let's do washer around the x-axis. All right. So what if we take the functions y equals 6 minus x squared and y equals 2, and I want you to rotate that black region, the black shaded region, by around the x-axis. So we're going to take this big region right here, and you're going to rotate it around the x-axis. Now, obviously, there is a big gap right there, so that is what's telling us to do the washer method. So once again, the washer method would be pi times the integral from a to b of your outer radius squared minus your inner radius squared. And since we're going around the x-axis, we're going to do this in terms of x. Both of our functions are already written as y equals, so you don't have to do anything special there. You can go ahead and go directly into setting this up. This would be pi times the integral. Now here's where you can be smart. Technically, you could just integrate this from -2 to 2, and that would be just fine. But what some of y'all may notice here, and I actually like to do symmetry a lot, is that if I were to take this region right here and find that volume, you could double it to get the other half of your volume. So I'm actually going to use symmetry here. So I'm going to integrate from 0 to 2, and then I'm going to double that region and take care of my parameters a little easier, because having a parameter of 0 makes things a little nicer. Now, once again, you don't have to do it that way. If you had just left it as -2 to 2, you would not have doubled it, and you would get the exact same answer in the end. So based on the axis that you're rotating around, the function that is the furthest away from the x-axis is the quadratic, which is 6 minus x squared. And I'm going to square that whole thing. And I'm going to subtract from that the inner function, which is the straight line, would be 2, which you have to also square. All right, so I'll bring this down. That would be 2 pi times the integral from 0 to 2. You would need to FOIL 6 minus x squared by itself, which would be 36 minus 12x squared plus x to the 4th. And then I would subtract from that 2 squared, which is 4. Putting your constants together, you would get 2 pi times the integral from 0 to 2 of 32 minus 12x squared plus x to the 4th with respect to x. Go through and integrate all of those pieces. So this would be 2 pi times, so let's see, that integrates into 32x minus 4x cubed plus x to the 5th over 5, evaluated from 0 to 2. If you plug your parameter of 2 in, let's see, 32 times 2 is 64. 2 cubed is 8, and 8 times 4 is 32, plus 32 over 5. And I'm not even going to worry about plugging the 0 in, because plugging the 0 in, you're not going to subtract anything off. So don't worry about it, but you can if you want to. So this would be 2 pi times 64 minus 32 is 32. And we're going to add 32 fifths to that. Getting common denominators. Let's see, 32, if you put a 5 on the bottom, that would be 160 over 5 plus 32 fifths, which would be 2 pi times 192 over 5. And if you double that parameter and put the pi in there, you should get 300 and, mental math here, 384 pi over 5. A lot bigger volume that time, but that is how you would do a washer method around the x-axis. So it's still the outer radius squared minus the inner radius squared, but you have to base it off which axis that you're rotating around. All right, to wrap up this section, the last couple of problems we have to do are probably the trickiest ones, because now we're going to talk about how do you rotate around a line that's not an axis. So on this first example, if you have y equals x cubed and it's bounded by y equals 1 and x equals 2, can you rotate this region around the line y equals -3? So the first three parameters actually give you this black shaded region right here. But you're not just rotating around the x-axis, you have to rotate it all the way around that line y equals -3. Now, when you rotate around a line that's not an axis, there's a little extra you have to do when it comes to your radius function. So here's a little bit of extra I'm going to add up here at the top. If the line you are rotating around is either, let me write this, is either above or to the right, because it depends on whether you're going around x's or y's. If your line you're rotating around is above or to the right, you are going to do the line minus the radius. Now that's not this example. The line we're rotating around is below, but on the next problem, we're going to see this one. If you are rotating around a line that is below or to the left, you have to reverse order, and your function would be the radius minus the line you're rotating around. So we'll keep that up there, and we're going to see this on the next two problems. So as far as our picture goes, obviously the shaded region and the line you're rotating around has a big gap. So we're going to end up doing the washer method here. So when I set this up, my volume will be pi times the integral. Now, since y equals -3 is parallel to the x-axis, you are going to do this in terms of x. So on the x-axis, we are going between 1 and 2. Since it's a washer method, you're going to have to do the outer function, outer radius squared. Now remember, your outer radius is going to end up being this general formula. You have to take the outer radius, which is the cubic function, so that's x cubed, and you have to subtract the line you're rotating around. And since you're rotating around -3, when you subtract a -3, it becomes +3. So that's going to end up being squared. Then you would subtract from that the inner function. Now this horizontal line here, which is y equals 1, is your inner function. And once again, when you subtract the line from that, you have to add 3 again and square it, and then we will integrate this in terms of x. So when you are rotating around a line that is not an axis, you're going to have to do a little bit of adjusting. Both your outer and your inner radius have to pick up the extra minus line term because you're having to shift the type of volume that you're doing. Other than that, the problem doesn't work any differently, because now you can set this up, foil it, and see what you get. So this would be pi times the integral from 1 to 2. If you square x cubed plus 3, that would be x to the 6 plus 6x cubed plus 9. And then you would subtract from this, 1 plus 3 is 4, and 4 squared is 16. All right, so putting those two constants together, we would integrate from 1 to 2 of x to the 6 plus 6x cubed minus 7 dx. And now we can integrate this. So this would be pi times, that would be x to the 7th over 7 plus 3x to the 4th over 2 when you reduce it, and then minus 7x, which we're going to evaluate from 1 to 2. All right, so plugging your parameters in. If I plug 2 into all of these, all right, let's see, 2 to the 7th. 2 to the 5th I know is 32, so do it 2 more times. That'd be 64. That'd be 128 over 7. All right, plus 2 to the 4th is 16. 16 times 3 is 48, and 48 divided by 2 is 24, and then minus 14. Subtract from that, go through and plug 1 into everything, which would be 1/7 plus 3/2 minus 7. All right, got a lot of numbers to put together here because we didn't get a 0 this time, so that's fine. So this would end up being pi times 128 over 7. Those two to go together as plus 10. And then if I distribute the negative, it's minus 1/7 minus 3/2 plus 7. All right, so that would be pi times. Putting my sevenths together would be 127 over 7. Putting my whole numbers together, that would be plus 17 minus 3/2. And we're going to have to find some common denominators here. Actually, to make this a little bit easier, let's put the 17 in the, well, I guess it doesn't matter. We'll just find common denominators up front. It doesn't matter in this case. So my common denominator is going to end up being 14 here. So I need to get all these in 14s. So the first one and the last one are a little bit easier. If you double 127, that's going to give you 254. On the last one, times 7 would be a minus 21/14. Then I got to do a little scratch work. If I want to do 17 in terms of a 14th, I got to multiply 17 times 14. So 8 and 2, that would be 6. That would be 7 and 1. So 8, 13, carry the 1. So that is 238 over 14. And then you've got to put all of those numbers together. So this would be pi times, let's see, 254 and 238 added together would be 12, carry the 1, that's 9. So 492. And then 492 minus 21 is 471 over 14. So you get a final answer of 471 pi over 14. The more abstract you make these problems, like when you start rotating around different axes, the volumes can get a little bit ugly. So make sure that you are careful when you're doing your homework on being able to do this basic arithmetic. Like I said, all these problems that I'm doing in class, I'm not using a calculator. So if you have to, don't be ashamed like I did. Come over and do a little bit of arithmetic to make sure you can get through this. So there's your first example of rotating around a line that's not one of the axes. Let's do one more just like it. All right, so example number 6 says, find the volume of the solid obtained by rotating the following region. But I added an extra thing here. Be careful of your parameters. All right, so this one is x equals y squared and x equals 1 minus y squared. And we want to rotate this red region around the line x equals 3. All right, so this line is to the right of the region you're trying to bound. So when it comes to our new radius, you're going to have to do the line minus the radius when we set this up. And once again, we're going to set it up as a washer method because there is a big gap in the shaded region and the axes you're trying to rotate around. So when I set up my washer method, this would be volume equals pi times the integral. So here's the challenge. When you look at this, since we're rotating around a line that is parallel to the y-axis, we have to do this in terms of y, which means these two little intersections right here, you have to find the y value that you get. Now, those may look like that they're 1/2 and -1/2, but they are not. So we're going to have to actually be sure what those numbers are. These 2 points right here will exist when the two graphs equal each other. So what I'm going to do is I'm going to take both functions from the beginning, the y squared and the 1 minus y squared, and I'm going to set them equal to each other. Because if I move the y squared over to the left, I would have 2y squared equals 1. Dividing both sides by 2 gives me y squared equals 1/2. And if I take the square root of both sides, I would get that y equals plus or minus 1 over root 2. Now, once again, you can integrate. Those are your two parameters. You can plug both of those parameters in your integral, and that's fine. But since this one is really ugly, I'm actually going to take advantage of a little symmetry here. Because if I were to just find the volume of the top half of this, I could double it to get the whole volume of the object. And it's going to be a lot easier to go from 0 to the positive parameter in this problem. So what I'm going to do is I'm going to integrate from 0 to positive 1 over root 2, and I'm going to double that region just to try to make this as the best as I can. All right, so now as far as washer method goes, you need to do your outer function. So if you look at the line you're rotating around, this red graph is the function that is the furthest away. So since that parabola is opening to the right, the red graph is going to be y squared versus the blue graph, that's going to be the 1 minus y squared. So since the furthest function away, which is your outer, is y squared. Remember, don't forget your new parameters because you're having to do a different line. This would end up being 3 minus your outer radius, which is y squared, and we will square the whole thing. And then you'll subtract from that 3 minus your inner radius. So if you subtract the 1 minus y squared, it becomes minus 1 plus y squared, all squared with respect to y. So that one is a little bit different. That's a little bit harder one to set up. But now that we have it set up, we can continue. This will be 2 pi times the integral from 0 to 1 over root 2 of 3 minus y squared all squared minus 2 plus y squared all squared. You need to FOIL both of these, so you would end up with 2 pi times the integral from 0 to 1 over root 2. If you FOIL the first, you will get 9 minus 6y squared plus y to the 4th. And then minus, if you FOIL the second pair, you will get 4 plus 4y squared plus y to the 4th dy. So we're going to distribute this negative through and then put together what we can. So this would be 2 pi times the integral from 0 to 1 over root 2. We're going term by term here. 9 minus this 4 will give me a 5. Negative 6y squared minus 4y squared would give me a negative 10y squared. And then the best part of this problem is that y to the 4th minus y to the 4th cancels, and you can just integrate those two terms. So if I go through and integrate, this will be 2 pi times, that's going to be 5y minus 10y cubed over 3, evaluated from 0 to 1 over root 2. So plugging my parameter in, now just like earlier, you don't even need to worry about the 0 because subtracting 0 won't do anything. If you just plug the 1 over root 2 in, so this would be 5 times 1 over root 2 minus 10 times 1 over root 2 cubed divided by 3. All right, so this would end up being 2 pi times, that's 5 over root 2 minus 10. If you cube 1 over root 2, that would be 1 over 2 square roots of 2. All of that divided by 3. So this would end up being 2 pi times 5 over root 2 minus 10 divided by 2 gives me a 5. So this would end up being 5 over this root 2 that's left over, and the 3 on the bottom would go together and make that 3 root 2. And now you've got to get common denominators to put these together. So if I put a 3 on the bottom of the first fraction and multiply by 3 on top, I can rewrite this as 2 pi times. There's going to be a 3 root 2 on the bottom. 3 times 5 is 15, and 15 minus 5 will give me a 10 on top. And then finally, you multiply this by 2 pi, and you get 20 pi over 3 square roots of 2. And that is the volume of that little red shape rotated around the line x equals 3. So there's an example of another one where you're rotating around something other than the axes. Remember, if you are above or to the right, the line you're rotating, you have to do the line minus the radius function. If you're below or to the left, you do the opposite, and it's the radius minus the line. So that ends the video for section 6.2. We covered the disk method and the washer method of volumes. In the next video, we're going to do one more technique of volume called the method of cylindrical shells.